Hi everyone, my name is Lim Yi. I would like to present my final year project title called Development of Fire Protection Duct for the Safety Relevant Circuits. Why we need to put the electrical cables inside the fire protection duct? This is because the cables are used to transmit the electricity to the fire protection system. For example, the fire alarm, the water sprinkler. Therefore, we have to ensure that all the fire protection system can carry out their work without any disturbance during the fire outbreak. In this research, the fire protection duct was assembled by fire retardant boards, and the fire retardant board was made up by water-based into meson binder, or what we call WIB as the short form. The reasons why we need to implement the WIB instead of using the commercial fireboards in the market are because the non-halogenated materials used in the WIB release a lesser amount of the toxic gas, smoke, and carbon dioxide gas as compared with the commercial fireboards. Other than that, the WIB offer a lower cost, which is about 7 ringgit and 20 cents, while fabricating a 175 times 175 times 30 of the fireboard, which is lower than the commercial fireboard that costs up to nearly 10 ringgit and 40 cents. In this research, the aim and the objectives are to formulate the WIB and develop the fire retardant board for the fire protection duct. And then we will determine the performance of the fire protection duct in terms of fire resistivity, water resistivity, sound insulations, and mechanical properties. Other than that, we will also like to analyze the characteristic of the WIB sample by using scanning electron microscopy analysis (SEM), energy dispersed X-ray spectroscopy (EDS), thermal gravimetry analysis (TGA), and Fourier transform infrared spectroscopy (FTIR) test. Now I will discuss the methodology and the work plans of this research. First of all, we have to sample characterize the WIB by conducting Bunsen-burner test, static immersion test, adhesion strength test, SEM and EDS analysis, TGA test, and FTIR spectroscopy test. After that, we will sample characterize the prototypes by carrying out half-hour small-scale fire test, density measurement test, impedance tube test, and three-point pressure test. Among all the prototypes, the leading performance of the prototypes, especially in half-hour small-scale fire test, will be chosen to compare its fire resistivity with the commercial fireboards by conducting 1-hour small-scale fire test. Lastly, the best performing fire retardant board will be chosen to assemble the fire protection duct and carry out 1-hour small-scale fire test in order to determine the ability of the fire protection duct in protecting the electrical cables during the fire test. Attached here we shows all the chemical compositions of the samples and the prototypes. The only difference between the sample and the prototype is the inclusions of the vermiculi. The additions of the vermiculi can help the prototypes to enhance or prolong the fire resistivity, especially in 1-hour or half-hour small-scale fire tests. There were so many testing methods have been conducted in this research. Now I will discuss some of the important testing methods. The first one goes to Bunsen-burner test. Basically, the Bunsen-burner test allows us to determine the temperature profile achieved by each of the samples throughout the half-hour Bunsen-burner test. We will also like to determine the expansion rate of the char layer achieved by each of the sample. One of the properties that the WIB is that the release of the char layer. As you can see in this small picture, the dark color hairline structure is what we call the char layer. This kind of the char layer can be served as the fire protection barrier that helps to protect the underlying substrates by resisting or reducing the penetrations of the hot flame throughout the fire test. After we conducted the Bunsen burner test, we will collect some of the char layer from each of the samples and undergo SEM analysis in order to determine the surface morphology of each of the samples. Besides, the static immersion test allows us to determine the water resistivity of each of the WIB by measuring the difference in terms of weight of the WIB. We will conduct this test to calculate the difference in weight of each of the sample by measuring the weight of the WIB before and after immersed in the water. Furthermore, the sound insulation test allows us to determine the sound absorption coefficients of the WIB. In other words, the higher the sound absorption coefficients, the better the ability of the WIB to absorb the sound, the lesser amount of the noise will be released to the surrounding. 3-point pressure test allows us to determine the pressure strength and pressure modulus. The higher the pressure strength, the higher the amount of the forces the prototypes can be withstand. The higher the pressure modulus, the higher the prototypes can resist to the bending. Lastly, one of our small-scale fire test allows us to determine the ability of the fire protection duct in protecting the electrical cables throughout the 1-hour small-scale fire. Now I will proceed to the results and the discussion. For the Bunsen burner test, as you can see, the blue color indicates the temperature profile achieved by sample number 4. So sample number 4 having the greatest ability to provide the lowest temperature profile throughout the half-hour Bunsen burner test. This is because the EG, the expandable graphite, will reduce the burning rate by generate a thicker char layer among the others, and the CES, the chicken eggshell powder, undergoes decarbonation process by release a certain amount of the carbon dioxide to reduce the penetrations of the hot flame through the structures of the char layer. After that, the SEM analysis allows us to determine the number of the pore found on the surface of the char layer for each of the samples. As you can see, the orange color indicates the number of the pore on the surface of the char layer. So, sample number 4 having a lesser amount of the pore as compared with samples number 1, 2, and 3. Thus, one can be proved that sample number 4 displays a denser structures and a uniform foam structures that can attach rigidly to the substrate. This is the reason why sample number 4 having the greatest ability to provide the lowest temperature profile throughout the Bunsen burner test. Next, the static immersion test allows us to determine the water resistivity of each of the samples by measuring the weight of the samples before and after immersed in the water. So, as you can see from this graph, the blue color and the green color provide a lower weight change percentage as compared with other samples. So the blue color and the green color indicates sample number 4 and sample number 3 respectively. The reasons why they will absorb a little amount of the water as compared with other samples is because the chicken eggshell found inside both of the samples exhibit poor water absorption property. This is the reason why they will absorb a lesser amount of the water, thus provide a better resistivity in terms of water. Besides, sound insulation tests allow us to determine the sound absorption coefficient of the WIB. The other researchers stated that the commercial gypsum board exists in the market has a sound absorption coefficient of 0.1. Therefore, one of our target in this research is to make WIB to achieve a higher sound absorption coefficient, which is more than 0.1. So as you can see from this table, the average sound absorption coefficient achieved by the WIB is 0.21. So it is been proved that the WIB has a higher properties and higher ability to absorb more sound and provide a lesser amount of the noise to the environment. Furthermore, three-point flexural test allows us to determine the flexural strength and flexural modulus of each of the prototypes. So after we conducted this test, prototype number 4 has been found to have the highest flexural strength and flexural modulus, which is 2.23 megapascal of the flexural strength and 53.55 Newton per millimeter square of flexural modulus. In other words, prototype number 4 having the greatest ability to withstand the highest force, which is goes up to nearly 477 Newton. When we look back to prototype number 1 and prototype number 2, both of them having a lower flexural strength and flexural modulus as compared with prototype number 3 and prototype number 4. One of the reasons is because prototype number 1 and prototype number 2 exhibit damage during the fire test. Therefore, the high temperature will cause the material to become flexible. This is the reason why the flexural modulus achieved by prototype number 1 and prototype number 2 are lower than P3 and P4. Last but not least, 1 hour small-scale fire test allows us to determine the temperature profile on both sides of the fire protection duct and also its ability to protect the electrical cables throughout the 1 hour fire test. So while conducting this experiment, we attach both of the temperature sensor. One of the sensor is at right side of the fire protection duct. We name it as T1, and the other one is attached to the left side of the prototype of the fire protection duct. We name it as T2. So as you can see from this graph, both of T1 and T2 exhibit a similar temperature profile, and they're able to provide a temperature profile lower than 180 degrees C throughout the 60 minutes of the fire test. And the other more important thing is that the electrical cables, after conducting the 1 hour fire test, does not exhibit a serious damage on the surface and the integrity. So one can be proof that the fire protection duct having the ability to protect the electrical cables throughout the 1 hour small scale fire test. In conclusions, formulation number 4, or what we can see from the result of sample number 4 and prototype number 4, having the greatest ability to be served as the candidate to assemble as the fire protection duct. Attached here we shows all the results of each of the testing methods done by each of the samples, each of the prototypes, and each of the fire protection duct. In the recommendation sections, it is highly recommended that the next researcher can purchase a high performance flame retardant materials in order to improve the properties of the WIB, especially in terms of fire resistivity. Other than that, it is also recommended that to remove the cast iron mold after the shape of the prototypes have been formed in order to increase the drying speeds of the prototypes. So that's all for my presentations about my FYP title. Thank you everyone for your attractions.